Good afternoon and welcome to the 21st annual exhibit of hydrogen fuel cell technology. We've been around here for a long time, even longer, this technology. When we go back in history, Alessandro Volta discovered the battery, and within 2 weeks at the London Academy of Science, they discovered how to separate hydrogen and oxygen, and pretty soon after that, it didn't take long before they had their first fuel cell. Of course, PEM fuel cells are the engineer's favorite because they seem so simplistic, yet there's all sorts of complexities, and one of them is simply the cost factor. There are precious metals involved, platinum being one of the more common things that people discuss, and this is a market barrier. Reducing the cost of PEM cells means the vehicles that we can create with PEM cells, they're wonderful for mobile applications, become affordable. We have a specialist on this topic. We'll be talking to Alia Lubers, who's involved in catalyst manufacturing at Pajarito Powder, and she'll be talking about engineered carbon supports for low precious metal content catalysts. Stay tuned.
Thank you so much. Good afternoon. I'm Alia Lubers for Pajarito Powder. We are experts in manufacturing carbon-based materials for the PEM fuel cell, mainly on the cathode side. We have materials for supports and also as catalysts themselves. Today I'll be talking about our engineered carbon support for low loadings of our precious metal catalysts. Our mission at Pajarito Powder is to fundamentally change the economics of fuel cell catalysts. And how we achieve this is through abundant materials, mainly based on carbon. We started operations in 2012. Our IP goes back even further, based from patents out of the University of New Mexico. We are based in Albuquerque, New Mexico in the US, and have a very good relationship with the university. Since then, we have licensed more IP from other universities, and our future developments are funded by the US government through several grants. So let's start with a very simple picture of a fuel cell. We convert hydrogen fuel and oxygen from the air and produce water and electricity. Where these reactions actually take place is in the inside, so if we expand this out, we can see where the reactants actually interact, which is on the inside here, our membrane electrode assembly. Isolating that, we can see it's actually a very small part of the fuel cell where the reactants interact and the reactions take place here in the membrane electrode assembly. But mainly where the reactions actually take place is on this catalyst layer on the inside. So if we focus on the cathode catalyst layer, it's mainly comprised of ionomer and platinum on a carbon support. These three main components and how they are arranged and adjacent to each other is actually very important for creating the three-phase boundary, which is where the reactions actually take place. So at the three-phase boundary, you have ions, gases, and liquid water all interacting to make the reactions drive the electricity generation. So in order to drive the efficiency of the fuel cell, in order to convert your hydrogen fuel more effectively, optimizing this three-phase boundary is very important. So we have developed a product line to assist in developing an optimized three-phase boundary. Our engineered carbon support and our PHC 3000 line. These are intended to support a low loading of platinum and encourage high corrosion resistance. So the idea is to have only a small amount of platinum and be able to stabilize that platinum over the lifetime of the cell so you can have extended lifetimes. And the idea behind developing a good carbon support is to really drive those costs down. So the DOE target projections for the ultimate cost of a fuel cell system is $30 per kilowatt. Half of that is budgeted for the catalyst, which is pretty phenomenal. The reason for that is because platinum is so expensive. If we can drive the amount of platinum that we actually need, we can also drive the ultimate cost targets down as well. How we do this is to produce a carbon support that is highly graphitic, has a particular particle size, and also has particular pores, enabling this optimized three-phase boundary. How we produce these catalysts is by mixing organic precursors and pore formers, heat treating those, and we develop a very highly graphitic carbon. Our particle sizes are actually quite large for primary sizes. These are more along the sizes of secondary particles within the catalyst layer. However, we have really a very porous surface, and these pores are also interconnected. So being able to manipulate these properties, we can further optimize what our catalyst layer looks like and that three-phase boundary. Because of our synthesis process, we can actually tailor the particle size to the needs of the catalyst layer demands. Additionally, we can manipulate our pore sizes to optimize that three-phase boundary. So not only can we make 10 nanometer pores and 40 nanometer pores separately, we can make those in the same material. Our measurements show that our pores are in a highly network of connection, so we can access all parts of the material and be able to place the ionomer and platinum in the best way possible to make this catalyst most efficient. So I've mainly been talking about our support itself. It's mainly carbon and graphitic carbon with a little bit of metal and some nitrogen. In order to evaluate these materials for fuel cell catalyst supports, we need to put platinum on them. So we've developed platinum deposition methods and as well as in-house testing. In addition to getting some assistance from our partners. In this particular case, we sent 2 different types of support to our partners, and they deposited platinum. Our PHC 3010 is a less graphitic material, and our 3020 is a more graphitic material. Just in comparing our carbon surface area and our platinum surface area, overall, the less graphitic material, we see higher surface areas there. In comparing these 2 platinized materials in a 1.2 volt hold, we can see that our less graphitic material, the 3010, actually has a very high catalytic mass activity. However, over the length of the test, we see a drop in both mass activity and electrochemical surface area. The more graphitic material in the beginning has less mass activity, however, is more or less stable over the course of the test. So depending on your application, if you want a high mass activity in the beginning, a less graphitic support would be more advantageous. If you're looking for long lifetimes and keeping that platinum more stable, a more graphitic support would be more appropriate. So our partner sent us back platinized support so we could test it in-house. We use high shear mixing to develop our catalyst inks. We spray our GDEs and use a heated press to synthesize a 7-layer membrane electrode assembly. Our main evaluation for these types of materials is a carbon corrosion test, where in the beginning of the test we activate the catalyst, And then we have 5,000 cycles of start and stop simulation. We then activate it after our corrosion testing and have an end-of-life test after reactivation. Some results of that test comparing our support materials that have been platinized with a high-spec carbon on platinum on carbon, which is the commercial catalyst available today. We can see that our beginning of life kinetics are relatively similar to each other. However, after carbon corrosion, our support maintains similar kinetic activity, where for our high-spec platinum on carbon, we see some loss in activity. For our carbon support, we have some loss of some transport properties, but we see even more for the high-spec carbon, platinum on carbon. So if we want to talk about economics, if our support is able to contribute to the activity, and also so you can drop the amount of platinum in the next couple of years, this is a representation if we can reduce the amount of platinum needed by a third and still be able to stabilize it so we have longer device lifetimes. And eventually in 2020 and ultimately if we can drop the amount of platinum needed for this reaction by half, we can dramatically reduce the catalyst cost that is half of the contributor to the system cost. Because our materials are abundant and easily made, the scaling of our cost is actually quite dramatic. The more materials we can make, the more bulk materials we can buy, we can reduce our manufacturing cost almost to nothing. So that was a summary of our engineered carbon support, our PHC 3000 line. We also produce catalysts that are completely platinum-free, if that is what you're going for. So in comparing platinum on carbon catalysts that have a lot of platinum, which is what we see these days, what we are trying to achieve is similar performances, but really driving this cost down at scale. And how we strive to achieve that is by reducing the amount of platinum that is needed by having a robust and even slightly catalytic carbon support, or eliminating platinum completely. Thank you for your attention. I'd be happy to answer any questions, or we can have even more in-depth discussions at our booth, which is just at the corner over there.
Thank you. I'm sure we do have questions from the audience. Any takers? It's such an interesting and complex issue. One thing that occurred to me is, on the one hand, reducing platinum does reduce the costs. There are some people who have been discussing platinum costs in terms of how easily it's recycled. Do you also address that formality, which is a big formality? If you use your carbon support technology, is it easy to recycle the platinum?
That's an interesting question. I'm less familiar with how platinum is recycled, and we really are experts more on the carbon side. Mm-hmm. But yeah, I know that the platinum recycling is a big issue, and I think that there are programs that are being developed to address that.
Well, to my knowledge, it hasn't been solved. So this is why the reduction to 1/3 is just like a phenomenal game changer. Particularly, I suppose, for mobile applications.
Oh, absolutely.
Platinum is, again, I'm formulating the question, is so important when you're considering energy density, measured on, for instance, how many watts per cubic centimeter or inch or whatever. And that's also a question of weight. If you're having mobile applications, the smaller the stack. So this is why your technology is so important for the mobile applications, I take it, because it makes PEM cells affordable for the automotive sector.
Absolutely. We don't want just a couple cars to be produced because they're interesting. We want them to be in widespread circulation because they work well.
Yeah. And right now they're just interesting. They should be mass-produced.
They will be.
Yeah. And I suppose the final question is carbon technologies. There's a lot of industrial resources behind carbon manufacturing. This isn't only important because what happens if you do get an order of 50, 100, or let's hope 5,000
exactly.
cells. Is it possible to upscale to mass manufacture using your technique?
Right away, yes. So if anyone has those orders, please let me know.
Well, this solves a lot of issues. The automotive applications are on the road. It's been a pleasure talking to you. I've been talking to Alia Lubers, who's Catalyst Manufacturing Manager at, and it's pronounced with...
Pajarito.
Yeah, Pajarito. Yeah, I didn't want to give away my preference for drinks in the evening and so on, but that's a wonderful, Pajarito. Yeah, it's been a pleasure. Visit the booth D31 over in that direction, and we'll be continuing in a few minutes to the next talk.
Thank you so much.